Okay, hello everyone, and welcome back. We're going to start the last topic of this class, which is about manifolds and duality and all sorts of fun things about geometry. And today we're going to talk about one of the first ingredients, Thom spectra and the Thom isomorphism. So I realized that I only defined everything for complex vector bundles 1 month ago or so when I talked about vector bundles. And it turns out that I need real vector bundles now. But the proofs are really verbatim. So I hope no one is going to be scared by the definition of a real vector bundle and the fact that real vector bundles are classified by maps into BON or maps into the Grassmannian and so on and so forth. Because of course, not all manifolds have a tangent bundle, which is a complex vector bundle. That's actually quite rare. So real vector bundle they are. So, okay, let me start with a definition. So let X be a space and V over X a vector bundle. The Thom space of V, which I'm going to write as THB, is the pointed space given by the cofiber of the map B minus 0 into B. Well, 0 here, I mean 0 section. Of course, it's a copy of X sitting inside V. So let me first give you a sort of a more geometric description of this gadget. And then essentially the rest of the class is going to be an exercise in generalizing this description to wider and wider settings until we can prove the Thom isomorphism. And you see that the proof of the Thom isomorphism will be surprisingly simple at that point. So let me first give you a more geometric thing. So lemma. Now let's suppose that X is an actual topological space and V is an actual vector bundle. Like, although of course it depends only on the homotopy type. But THV is equivalent to the 1-point compactification of V based at the point at infinity. You'd all have seen the 1-point compactification at some point in the past. It's just every time you have a topological space, you can get a compact space by adding a point and putting a certain topology saying that the neighborhood of that point, a set is an open neighborhood of that point if and only if its complement is compact. But it's not really important. Essentially, what we are going to need is that the 1-point compactification of R to the n is S to the n, which should.
So there, how is V pointed, or how do you get the pointing of the Thom space in the definition?
It's a cofiber. It's a mapping cone. I'm pointing at the cone point.
Yes.
If you want, okay, let me actually write the cofiber diagram. You have a square like this, and the pointing is this bottom arrow.
Yes.
Or if you think of the cofiber as a mapping cone, it's pointed at the cone point. Cofibers are always pointed. That's a useful fact that we'll use in a second, actually. But first, this concrete lemma. In fact, this lemma is the traditional definition of the Thom space. Although it will be more convenient and more canonical to think of it as that cofiber. So proof. Since I don't want to do it canonically and I don't particularly care about doing canonically, let's choose a metric V, by which I mean it's just a map from V to the positive real numbers, which is a norm, sorry, which is induced by a scalar product. On each fiber. If you want a quick way of doing that, given what we've done so far, but it's a bit of an overkill, but whatever, is that you have V lying over X. We know that it can be represented by some map to B or N. We choose one, and we choose a nice diagram so that it's a pullback. We can do that. We've proven that every vector bundle can be obtained like this, and this guy has a metric. Since psi n is Vx in R infinity times x, such that, so sorry, not BON, I mean it is BON, but let me call it like the nth Grassmannian. Such that V is in f of x, where f is this map. And you can just take the norm in R infinity, and this gives you a nice scalar product on each fiber. In fact, with some effort, you can turn out to prove that the choice of such an f is equivalent to the choice of a metric. Plus, eventually, it's not important. Anyway, you can do that. There are also simpler ways of doing that using partitions of unity and so on and so forth. But you can do that. And so note that V minus 0 then is equivalent to the unit sphere, which is V in V of norm 1. That's because you have, well, you clearly have an inclusion here, but you have an inverse map here sending V to V modulo the norm of V. And that's, well, you do a straight line homotopy. This gives you a homotopy equivalence. On the other hand, V is equivalent to X. Just the projection at the level of underlying space is just an equivalence. I am just collapsing everything to 0. I have an inverse map that's exactly the 0 section. Because the underlying space of a vector bundle is not particularly interesting. So the cofiber of V minus 0 into V is the same thing as the cofiber of S of V mapping to X. Since I'm just replacing the spaces with equivalent spaces. And here I'm taking the mapping cone of this map. And I'm going to show you that this is exactly the one-point compactification. So remember, how does this work? Well, the cofiber is the mapping cone, so we can write it like this. Is this iterated push out. As we have seen last semester, the cofiber can be explicitly computed as the mapping cone. And as I said before, this is pointed here. This cone point that I'm adding. And I claim this is exactly what I'm going to call SV, that is the 1 point, no, sorry, not SV. And this is claim exactly this equivalent to the 1-point compactification of V. And to do so, let me construct actually a map from, take a map from SV times 0, 1 to the 1-point compactification of V. And actually, it's probably easier if I construct a map from SV times the half open interval into V. And this is just going to be, oh geez, oh well, I chose the wrong. Direction doesn't matter, the formula is a bit more complicated, but the idea is you rescale V so that for t equals 1, you get 0. And as t goes to 0, this goes to infinity. So what's the... I think you need this formula. You just, the graph of 1 minus t over t, 0, 1, is just a hyperbola branch like this. So we're just rescaling. And so this clearly gives a map (0, 1) union SV times 1 x is a homeomorphism, actually, not just a map. With inverse is essentially sending V in the pair V over V, comma, whatever the inverse of this rescaling is. I think it's V plus 1 over absolute value of V, yeah. I hope I'm not screwing this up, but for 0, it goes to 1, and as the norm tends to 0, these also, no. Oh, no, sorry. That's, okay, that's much better. And as the norm tends to 0, these tends to 0. No, sorry. Okay, you know what? Let me not try to improvise this inverse. This is obviously an invertible function, so, pick the inverse. Sorry. I chose a different function in my notes. Oh, that doesn't matter. It's just, this is clearly a homeomorphism. And so these two spaces have the same one-point compactifications. Oh, sorry, I should have said one important thing. When X is compact, this is the one point. Otherwise, this Thom space is not compact, because you can lose pieces at infinity of X. Okay, and that's the proof. So you can think of, well, we'll see a much better way of thinking about the Thom spaces in a second. But you can think of this Thom space as sort of a generalization of how you make Sn out of Rn. You add a point at infinity. And here you have a vector bundle, and you add a point at infinity. That's the same for every fiber. Now, if the base space is compact, this tells you that you're just one point compactifying everything. If the base is not compact, well, of course, you might lose stuff in going at infinity in the base, but you're still adding a point at infinity in each fiber. And one way of describing this is that you are one point compactifying each fiber and then collapsing the 1 points you've added. And that's the kind of perspective I want to describe now. But first, a corollary out of this. Well, okay, that's not a corollary. Let's do it later, because this works only when the bases are compact. Well, the corollary I want to state is true for all bases. So let me state it after I can prove it. So, okay. Here's the following lemma. So let P from V to X be a vector bundle classified by some F from X to B O N. Actually, okay, I'm fixing the rank here, but it's actually irrelevant. Actually, maybe I should say disjoint union B O N. since I can allow different ranks on different connected components of X. Then the Thom space of V is the colimit of the composite X goes to disjoint union BON goes to spaces pointed where BON into spaces pointed is given by the ON action on Sn, seen as the one-point compactification of R to the n. So if you want, BON maps to, no, that's not. So this is seen as the one-point compactification of R to the n. And this, of course, fixes the point at infinity because it's just acting on R to the n, whichever, and fixing the point at infinity. So that's the point. You can think of this as a functor, this composite functor. You can think of the functor as the functor that sends X to the one-point compactification of Vx, which I'm going to start writing as SVX. So let me use notation. Real vector space. SV is going to be the one-point compactification.
I'm always bad with this. Can you recall what ON is? So
ON, sorry, is just m-dimensional orthogonal group. If you want matrices in M and R such that this is the identity. Or if you want linear endomorphisms that preserve the metric, or I don't know, choose your favorite description for this thing.
Excuse me, Denis, could you go once more on how this action on Sn gives a map from BON to spaces?
Yes. So let me be precise, actually. So remember, now I need to define you how, I need to go back to how we defined the infinity category spaces star. So spaces star, remember, I was defining it as the simplicial nerve of Can star.
Okay, right.
That's not the only possible way, but that's the one I've chosen in this class. And the point is that ON gets you a map into continuous maps preserving the base point from Sn to Sn. Remember, this was the Can complex whose n simplices were maps like, oof.
Yeah, I mean, this I can believe.
And this preserves composition. This is actually a map of topological monoid. Well, sorry, of simplicial monoids, since I define it only as a Can complex. So, okay, let me actually be super precise and here saying that I'm putting Sing. So what I have a map from the topological delta n into ON, and I want to get a map from Sn times topological n to Sn that preserves the base point at each stage. But okay, that's
but this is actually okay. I was wondering what happens next. I mean, if you have this map, then
okay.
Then you use
okay, sorry, BON, I should say it is, I don't remember if I gave it as an exercise. I think I gave it as an exercise at some point, maybe for ON discrete. But BON is actually the same thing as the simplicial nerve of the Can enriched category with one object and seeing ON as endomorphisms.
Oh, okay.
Because, well, what is this guy? This guy is a connected space with ON as loops.
Right.
Okay, this guy is
Okay,
definitely
so
a connected
yeah, this was
space.
the missing piece for me. Okay.
This guy is clearly a connected space. And you compute its loops, and its loops is exactly On by a single n, I guess, if you want.
Mm-hmm.
Okay, I think I gave it as an exercise. I'm not sure I remember. Maybe I did it only for G, a discrete group, though. But the proof is the same.
Okay, great. Thanks.
Okay. Other questions about this point? No. Okay. So let me decrease in size this thing and put it somewhere where it doesn't. Well, I don't have a good place to put it. But okay, I want to go back here and try to give you this, why you should believe this. This is, how do you compute the limits in pointed spaces, the colimits in pointed spaces? So you compute the colimits in spaces, and then you get the colimit indexed by the constant factor at the base point, and you have to collapse it. Remember, we discussed this a long time ago. So what is this colimit? You're literally 1 point compactifying each fiber. So replacing Vn by SVn, by this 1 point compactification. And this gives you what's called a spherical fibration, a fiber bundle whose fibers are spheres, together with a section, a copy of X. And what you're doing, okay, I'm collapsing this copy of X just to a point. And that's exactly what the Thom space is doing. Okay, and the proof of this lemma is actually essentially what I said, only said better. But the important fact is that you understand the intuition about what the Thom, and I think this is actually the best description of what the Thom space is. You are 1 point compactifying each fiber and then collapsing all these points you added to just a single point. Okay, so proof. Are there questions about the statement before I prove it? No. Okay, so the first, as before, well, okay. So let's consider V minus 0 goes to X. This is a fibration. This is a fiber bundle. In particular, a fibration. So, in particular, V minus 0 fiber product over X of the little point in X is exactly the fiber minus 0. When here I'm taking homotopy pullbacks. That's because when one leg is a fibration, the homotopy pullbacks is literally the classical pullback. Now, notice that X, we can write X as the colimit of X, of little x. This is a game we're going to play. This is essentially the universal property of the colimit, if you unwrap it. I think I used it before, but if not, I'm going to use it several times. If you take the colimit of 1 point indexed by a space, well, whatever you're going to get the space. The homotopy colimit, of course, is not true for one colimit. I mean, it doesn't make sense for one colimit in spaces. And now, therefore, by descent, you have the colimit over X and X of this pullback is just, I can move the pullback out. This was one of the key property of colimits in spaces. And so that's just V minus 0. Okay, so we want to compute the colimit for x in x of vx minus 0 to, well, okay, the colimit of vx. I can do the same goal for vx, or I can just notice that vx is contractible, so it's a pointer, so it's just sort of cosmetic that I'm writing v instead of x in this formula. Sorry, the cofiber of this map of colimits. And now the key point is that I can take the colimit out. So we have a map, cofibers from arrows in spaces to pointed spaces. And this is a left adjoint. It's the left adjoint of the functor sending a pointed space x to the arrow. Point mapping to x. And that is the universal property of the cofiber. Right, you have a map YZ going here. That's the same thing as a map of pointed spaces from the cofiber. So I call this F into X map of pointed spaces. That's the universal property of the push out. So the cofiber is a left adjoint. In particular, it commutes with homotopy colimits. So the Thom space of V, I can move the colimit out and get the cofiber Vx minus 0 into Vx. And this cofiber is, by the same argument, if you want, it is literally the argument for the Thom space over a point, which is undoubtedly compact. This is exactly the one-point compactification of Vx. And the functoriality, and this identification that I wrote is absolutely functorial in the vector space V. Remember, a functor out of V O n, you can think of it as vector space equipped with a metric, actually, because that's why I chose O n. So this is colimit. And here's the trick that I am taking the colimit in pointed spaces. Otherwise, the cofiber would not be a left adjoint, and this formula wouldn't work, as it shouldn't, because the colimit in spaces has a whole other line at infinity that I need to collapse to get the Thom space. Okay, other questions? No. Okay, so from now on, I'm actually secretly taking this as the definition of Thom space. So for example, let me define a rank n spherical fibration is a functor from x to pointed spaces, let me call it S, such that S of x is equivalent to Sn for every x, non-canonically, of course. And you can do, an arbitrary rank spherical fibrations. And we can define the Thom space of a rank n spherical fibration as the colimit. And arguing as I did before, you can think of this as a fiber bundle with fiber Sn together with a section that gives you a base point at every point. You might ask, okay, can't I just take instead the unit sphere bundles? This seems a lot more natural as a definition of a spherical fibration. And the answer is yes and no. Yes, in the sense that you can define such a fiber bundle of fiber Sn-1. That's definitely allowed. And from that, you can get a Rankine spherical fibration in this sense, but the vice versa is not true. It's actually a complicated problem in geometric topology. You cannot always fill it to a disk bundle, which is something we need to do here. And so this is more general, and I'd rather work with this for various reasons. Okay. But we're going to generalize it further. However, before I generalize further, let me give you an example of that's interesting, at least of these gadgets, because I'm talking about vector bundles because secretly I'm thinking of smooth manifolds. But these Rankine spherical fibrations are useful because they allow you to talk also about topological manifolds without having to worry about linearizing. So let me give you an example of the tangent spherical fibration of a topological manifold. So example, let M be a topological manifold of dimension n. Then the tangent spherical fibration is the functor M to pointer spaces, sending X to the cofiber of M minus X going to X to M. Okay, I have to tell you two things. I have to tell you why this well-defined and why is this actually a spherical fibration. Why this is well-defined, it's easy because I'm going to trick these and as writing it as a pullback again, I'm taking M times M minus the diagonal copy of M fiber product over M of X. And as before, you can see that these actually give me a functor. If you believe in the existence of a natural transformation, well, you should believe it. Anyway. So this is actually a natural transformation from the point to M. If you believe in the existence of such a natural transformation, which is just, if you want, the diagonal section of this, induced by the diagonal section of this fibration, and then you believe in the existence of this guy. So this is indeed a functor that I'm telling you. And now we just need to check that for every X, this is a fiber. Yeah, this is a sphere. But remember that when you had open coverings, this gives you homotopy pushouts. This we discussed last time. So recall the open subsets. You have this guy is a homotopy pushout. And so we are going just to take a small neighborhood of X that's homeomorphic to R to the N. So now take U inside M, neighborhood of X homeomorphic to R to the N. This tells us that we have the following homotopy push out. I'm taking U and M minus X as open covering of M. That's of course. So now we have our M mod M to the X here. And here we have U mod U minus X, and these are homomorphic because co-fiber of parallel arrows in a homotopy push out square are homomorphic. And this is homotopy equivalent to Sn. This is Rn mod Rn minus 0, and as discussed before, this is just S to the n. So this is indeed the tangent bundle. And I think I'll leave it as an exercise. If M is smooth, this is equivalent to X goes to S to the 1-point compactification of the tangent bundle. That's because you just take a tubular neighborhood of the diagonal inside M times M and do the same trick again. And use, I don't know, maybe the, tubular neighborhood of the diagonal is enough. You need to know what the normal bundle of the diagonal is. But if you know smooth manifolds, that's an easy exercise actually. Then tubular neighborhood of the diagonal is the normal bundle of the diagonal is indeed the tangent bundle of your manifold. Actually, I think I can put this as on the exercise sheet actually, even if I basically gave you the solution now. But writing it down is interesting. So you see, this is a generalization of the tangent bundle. Of course, it's not a vector bundle anymore, but if your manifold is not smooth, you don't expect it to be able to linearize stuff locally, because being able to linearize things locally is exactly being smooth. In fact, you can do something better. You can, this is a spherical fibration, but you can actually upgrade it to what's called a microbundle, which has a little bit more structure. Although I'm not going to do that. But it is the first, this is the first question. If you have a space with a spherical fibration, can I turn it into a topological manifold? The first question is, okay, can I take the spherical fibration into a microbundle? And for a smooth manifold, can I take the spherical fibration into a vector bundle? This is the subject of surgery theory, which I'm not going to discuss in this class, unfortunately, because it's a very fun topic, but this is the time we have. Questions about this example? This an example is going to be important because as you might not be surprised by, this is indeed the thing that's going to control the orientation in for Poincare duality, for a Tia duality, actually, I should say, the spectral version of Poincare duality. I think it's a fun example. It is very easy to define, and it does give you a notion of tangent bundle for general things. Yes?
I'm still confused. Why do we have to define M minus X as this pullback? And just...
Sorry?
Why do we have to define M minus X as this pullback and can't just work with M minus X?
Oh, it was just to convince you that this is really functorial. If you believe me that it's functorial, then it's okay. Yeah. It's just that I don't want to pass too many details under the rug, even if they're kind of standard and obvious, but it's still, you know, so it's always good to be a tiny bit precise. Since I'm being functorial on an infinity groupoid here, which might be still a bit confusing. And the trick usually for these things, you build something as a fibration where, you know, where taking the fibers of a fibration is always quite clearly functorial. Okay?
Thanks.
Okay. Okay, so now let me define the main subject of today. which is, so if S from X to space star is a spherical fibration of whichever rank, the Thom spectrum of S is just the suspension spectrum of sigma infinity, of Thom S. So I'm going to write it as X to the S. And when S is going to come from a vector bundle, I'm going to call it X to the V. I hope I'm not going to have to write X to the S to the V, because that's kind of a waste of superscripts. Anyway, it's the and that therefore this is the same thing as the co-limit over X in X of sigma infinity S of X. Since sigma infinity is a left adjoint, and so it commutes with homotopy co-limits. And this actually suggests us to take a further generalization of this notion of Thom spectrum to the level, to the notion of stable spherical fibrations. So definition, a stable spherical fibration is essentially the same thing as a virtual vector bundle compared to a vector bundle, but I'm going to write it. This is a functor X goes to sp, I'm still going to call it S, such that S of X is equivalent to some suspension of the sphere spectrum for every X. And N will be locally constant necessarily, and I'm going to call it the rank of the stable spherical fibration. And the Thom spectrum of a stable spherical fibration is just its co-limit. And I'm still going to write it XS. Yeah, you should have all the time to discuss orientability. So let me give you some examples first. So for example, so you know that you have a map for every n, you have a map from BON to pointed spaces, sorry, to spectra that sends the point to the sphere spectrum. You can write this as the composite of this map. So this one is the one sending the action of ON on Sn, and then you send it to spectra, and this is sigma infinity minus n sigma infinity, sigma minus n sigma infinity. Composite. And you can check quite clearly that this diagram commutes. Because the action of ON in Sn plus 1 is literally leaving its last coordinate invariant. Oh, I forgot to say, I should have said something about Thom spaces before. Well, okay, I'll say it after this example. So we have a map BO mapping into spectra. So I can form a stable spherical fibration from every virtual vector bundle. i.e., if I have a virtual vector bundle, say of rank 0, although it's not very important, to BO, a virtual vector bundle, remember, is a map to BO times Z. So I'm just taking the 0 component here. Sorry, let me call it V. I can form a stable spherical fibration SV, which is just this composition. And BO, I actually don't know what to call this thing. I think I'm going to call it J because it's related to the J homomorphism.
Excuse me, Denis, could you scroll a bit up just for a second? Okay, thanks.
I'm saying ON acts on SN, therefore it acts on its the suspension spectrum by functoriality. That's all what this first line is saying.
Yeah, I just wanted to copy it.
Yeah. Okay. Yeah. Let me pause a second so you cannot. Okay. Okay. Let me define one of the protagonists for the end of this class, which is MO is going to be the Thom spectrum of the universal virtual vector bundle. And in 1 second, I'm going to give you a description. But first, I have to tell you one thing about Thom spaces that I forgot to mention. But this definition should be clear, right? And since it was important in last talk, in last lecture, since I mentioned MU is defined as the Thom spectrum of the composite BU goes to BO goes to spectrum. So I promised you last time that I would define you such a spectrum, and now I did. And in fact, this is, if you think about it, is the universal Thom spectrum for a complex vector bundle, virtual complex vector bundle instead of a virtual real vector bundle. Since virtual complex vector bundles are the same thing as maps into BU. Okay, but first, unfortunately, I made a mistake and I have to put you a remark. So suppose that S from X to pointed spaces and S prime from X prime into pointed spaces are spherical fibrations. Then S mesh S prime, that goes from X prime to pointed spaces, ascends X prime to S of X mesh S of X prime, is also a spherical fibration. Because smashing two spheres is a sphere and the ranks sum. And in the case they come from vector bundles, this corresponds to the direct sum of vector bundles. And the Thom space of S smash S prime is the Thom space of S smash the Thom space of S prime. And that's because smashing commutes with colimits separately in each variable, since it has a right adjoint taken by the space of pointed maps. So we have the colimit over x prime, x times x prime of sx smash sx prime. This is the same as the colimit in sx smash colimit in x prime of sx prime. Is all I'm saying. And in particular, if I have a vector bundle, Thom space of V plus one copy of the trivial vector bundle is the same thing as the suspension of the Thom space of V. Because the Thom space of the trivial vector bundle over of rank 1 over a point is just S1. Thom space of R over the point is just S1. And V plus 1 corresponds to the external direct sum of vector bundles with this vector bundle. Okay. Okay. Let me give you 1 second to digest this. This is just pretty much what you would expect when you think about it as one-point compactification. If you take the one-point compactification of V plus V prime, that's the same thing as the one-point compactification of V smash the one-point compactification of V prime. Because it's just saying that, yeah, it works. And so let's try to describe MO. So this map BO to spectra is the colimit of functors BON into spectra and okay, and so MO, let me call this functors, let's say I call this functor J, let me call this functor Jn. So MO is necessarily the colimit of BON Jn over N. And we can write it actually, okay, yeah, but Jn is the nth desuspension of the stable spherical fibration associated to the tautological vector bundle psi n over BON. That was just by definition. And therefore BO, by the remark I just made, this is just the nth desuspension of the suspension of the Thom space of psi n. And note that this map from this guy to BON plus 1, Jn plus 1 is induced by this map. Coming from the fact that we have such a Cartesian square. That's because the tautological bundle is the universal bundle. So MO is the spectrum associated to the pre-spectrum Thom psi n. Because this is literally, by definition, it was colimit. The spectrum associated to a pre-spectrum is literally, sorry, minus n, is literally this colimit. And that's actually why I'm saying this. I'm saying this because this is probably the definition of MO that you'll find in most of the literature, certainly in most of the literature written before the year 2000. Actually, even earlier. I think this definition as a co-limit that I gave you is much more recent. It comes from a paper with 5 authors that I never remember. Endo, Gettner, Bresk, Blumberg, I think was also in the authors. I don't remember the list of the authors, but it's very convenient. It allows you to work with it much more neatly. As you will see, our proof of the Thom isomorphism is going to be much, much simpler. But I wanted to show you the connection with the classical definition. Okay, we'll basically, okay, no, I'm lying. In the very end, we will use this definition to do some stuff, but most of the class will not use this definition, but I think still sufficiently concrete. I gave you an explicit pre-spectrum given by explicit spaces, which you can think of as Grassmannian, and points. You can actually write down the points and the bounding maps. So this is not a very mysterious object. In general, perhaps I should mention that Thom spectra are spectra that are easy to describe. They tend to be very easy to manipulate and easy to work with. And as you will see now that we're going to talk about orientation and the Thom isomorphism, you'll see what I mean when I say that they're simple. Questions about these before I slightly change topic? No. Okay. So, okay, let me talk about orientations now. And I'm going to talk about orientation of stable spherical fibrations, since it's the generality in which we are working. But I will explain why this corresponds to the classical notion of orientations of vector bundles. So let E now be a homotopy ring spectrum. And this, actually, I was just complaining yesterday with a person that it would be so much simpler if I could work with an E infinity ring spectrum, even if you use something in generality. But all the examples we care about will be E infinity ring spectra. On the other hand, in this class, I never defined E infinity ring spectra. So I will just use homotopy ring spectra and follow the classical literature. This has the advantage that I will get some slightly more general results, although it's not completely clear how useful that additional generality is, but it will make some proofs a little bit more awkward. That said, you know, this is the thing that we have to work with. Okay. So for the rest of today, E is going to be a homotopy ring spectrum, and probably even homotopy commutative, by which I mean just an algebra object in H sp. So we have maps eta from S to E and mu E tensor E to E, satisfying associativity and unitality up to homotopy. Okay. So a stable, okay, an orientation or Thom class on a stable spherical fibration of rank n is a map, and sorry, this is an E orientation, I should say, because this notion depends on the ring spectrum that we're considering. It's a map from XS to sigma and E, and I'm going to call it theta, Tom, such that for every x in X, the map E tensor Sx. Sorry, no, the map Sx going to, and remember this is non-canonically equivalent to Sn, to Es, sorry, sigma n, to sigma n E corresponds to a unit of pi 0 of E. This is not dependent on the particular choice of identification here, of course. Since at the best I can change this, at the level of homotopy classes, at best I can change the sign of the element, and well, if you want, or if you wanted, or more canonically, to a generator of classes maps as a P0 module. This is a free pi 0 module of rank 1. This is, I'm using this notation for homotopy classes of maps. I think I used it before. This is canonically by choosing any identification of Sx with sigma and S. This is a pi 0 E module of rank 1. So it makes sense to say that an element is a generator. But I'm going to think of it in terms of unit of pi 0 E after doing an identification. Okay. In particular, the map E tensor Sx to sigma and E, which is obtained by multiplication. So actually, let me write it. Is an equivalence. Which is the important fact. Okay. Is this definition clear? Because I'm just about to write it in an equivalent way. And then we'll see a couple of examples when E is HF2 and when E is HZ. And we will see that this corresponds to classical notions of orientations. But now we're going to be allowed to have different and crazier ring spectra, or I guess maybe we're not much allowed, but okay. So remark, giving a map from this colimit is equivalent to giving a natural transformation Sx into sigma and x, where this is constant functor. And often we will think in these terms of a natural transformation from Sx to sigma and E, such that that product map is an equivalence. Okay, let me give you examples. Okay. If E is HF2, every stable spherical fibration is orientable, admits an orientation. In fact, it is in fact, you will see that by this description that the orientation will also be canonical. This corresponds to the fact that Poincare duality holds with mod 2 coefficients for no matter what manifold you have. Yeah, the condition of being orientable is empty for so this is a simple thing. Okay, let's see why. So the point is that the mapping space in spectra from HF2 to HF2 is the same thing as homomorphism of abelian groups from F2 to F2 by the recognition principle. If you recall, we discussed that abelian groups embeds fully faithfully into spectra. And so that's just F2. That is, we have the zero map and the identity and nothing else. And in fact, this is a discrete space even. So we can take what did I want to say? No, hold on. That's not quite what I wanted to say. What I want to say is the maps in spectra from the sphere to HF2 are equivalent to omega infinity of HF2, which is just F2 again. And so if we want to take maps from XS to HF, from say sigma n HF2, remember this is the same as limits from maps from Sx to HF2, and this is discrete with two objects. But moreover, we're not interested in random maps. We're interested in maps that hit a unit when the maps that hit a unit when you restrict it here. And this contains, so the space of Thom classes or of orientation is exactly the limit by taking the, well, let me call it the identity, or the maps that hits one, and that's just a contractible space. So, yeah. The space of Thom classes is contractible. In particular, it's non-empty, but even more, it's just a point. So an F2 orientation is no data. Questions about this example? I'm sorry, this is also a true fact, but that's not what I wanted to use.
Could you repeat just the last line?
So the space of Tom classes is the subspace of these maps, such that every component here corresponds to a generator, right? That's by definition. A Tom class is a point here. So I'm taking the limit, not of all maps, but only of the connected components that correspond to generators.
Okay, thanks. I think that clarifies it.
But that connected component is just a point. So it's not particularly.
Okay, and in the Z case, you will have 2 points which will ruin the thing.
Yes, I'm going to do the Z case now. I'm just going to do the Z case in 1 second. Further questions about the F2 case, though, before I do the Z case?
Yeah, so on the right-hand side, the mapping space, you forgot the end suspension, right?
Oh, yeah, sorry. Yeah, and I guess I should say that this, yeah, okay, this is the end suspension of S non-canonically. So, it's still a discrete space with 2 objects.
Because it's just a shift somehow, or?
Yes, yeah, sorry. I'll say that, maybe let me write it. Maps from S and sigma and F2 is the same. Since sigma is an equivalence, discrete space. In fact, it's just the space 0, 1. Literally, it's just a set with 2 objects, 0, 1. So in fact, I'm doing all sorts of non-canonical identifications here, but it boils down. I have a discrete set with 2 objects, one of which is 0 and the other I call 1. And so this identification is actually secretly as canonical as you can possibly have. You just don't have any space to have any choices here, which is what makes things work, of course. Does this answer your question? I'll assume it. I'll take it as a yes. Although maybe I shouldn't. Now let's say another example. So E equals HZ. And let me say it for a vector bundle. So you can adapt this easily to stable spherical fibrations, actually. But an orientation, let V be a vector bundle of rank n. An orientation, an E orientation, is the same thing as a null homotopy of the composite X goes to BON goes to BC2, where this map is the induced by that ON to C2. So I never use the formula for the determinant. What I'm going to use, in fact, is the projection on the pi naught of ON. But this is the determinant map. In particular, IE, the same thing as a lift to the fiber, which is what's usually called BSON. And then this is a classical statement that this corresponds to a trivialization of the determinant bundle, which is the classical notion of orientation. Maybe you've seen it in a slightly different setting. You can find a bunch of charts such that the gluing map for those charts are not in ON just, but in SON. Or if you want, another way of proving it is that BSON classifies vector bundles of rank n together with the trivialization of the determinant bundle. Doing the same proof that I did for BON. Well, actually I did for BUN, but the same argument applies. And if you've seen it in exercise sessions, the fact that maps into BG classifies G torsor, G principal bundles. That's another way of saying this is that a vector bundle together with an orientation in the classical sense is the same thing as an SON torsor, which is probably how people write it in the differential geometry, differential topology books. These are all different ways of saying the same fundamental content. But I'm going to claim that HZ orientations are the same thing as a null homotopy of this map. And in fact, this C2 here is secretly Z cross, the invertible elements in Z. So let's do here, we take maps from XV into sigma n of HZ. As before, this is the limit for X in X of maps of, well, let me denote, it's a bit abusive notation. This is the notation I told you for a space. I'm using it for its suspension spectrum, but to actually, no, let me be pedantically annoying and put sigma infinity SV, the sigma HZ here. And now notice that these, as I said before, this is on Z discrete Z module. So it's the Allman-McLean spectrum of a discrete Z module. Actually, it's H of a discrete, sorry, of a Z module of rank 1. A free Z module of rank 1. And so if I take the space, the subspace of Tom classes here, this is the limit of the set of generators. How should I denote this? Well, it's the set of generators of HN SVX, I guess. This is Z module of rank 1. Sorry, maybe I should mention this is exactly HN of SVX. Because the pi note of this small Z module of rank 1 is, of course, just the pi note of this mapping space, which many, many months ago, we noticed it was HN of the space. We reduced as HN. Actually, not that it changes anything, but we might be precise as long as we're doing this. And this is, again, canonically, you can identify it with 1 or -1. It maps from X sorry. Yeah. I wanted to say. Sorry, 1 second. Okay, the Tom isomorphism, I think I'll do it the first time next week, but let me finish this. Right, so this is the same thing as, so this is a functor. You can think of this as a functor from X to abelian groups of rank 2. Right, the generators of H tilde and SVX are an abelian group of rank 2. No, what I want to say. No, not to free rank modules. Free Z modules of rank 1. Yeah. No. Okay, let me see where I want to go, because the point is that this is the same thing as a map from X to BC2. Yes, sorry, that was silly. Another way of thinking it is functors from X to free Z modules of rank 1. Yeah. Sorry, okay, sorry, I'm kind of lost myself in this proof. I got a bit confused. Let me tell you how you conclude from these, the thing, and then I'll try to reconstruct 1 second this missing step. But the point is that, okay, once you have that, you can just look at, you want to identify this map. And yeah, the first observation is that ON acts on H tilde SVX via the determinant map. So this functor here that sends X to the set of generators of H and tilde SVX factors through BON, of course, and factors through the map the functor BON set that corresponds to the action of ON on the set plus or minus 1 by the determinant map. And Oh, of course, it's not maps. That's what I was trying to prove something false. Of course, the set of orientation is not the set of maps from X to BC2, but it's the set of null homotopies of that map. And I was trying to prove the wrong thing. I was trying to say that this map is an orientation, but a null homotopy of this map is an orientation. So, oh yeah. Sorry. Okay. Good. Let me. Sorry for this confusion. I was trying to prove the wrong thing. So let me step back. So we are all good here. That this map is this space is the limit over all x and x of the set of generators of this abelian group. But this, you can think of it as a functor from X to the category of free Z modules of rank 1 with a choice of generator. That's definitely, or if you want, with. But this is okay, this is a contractible category. This is silly, so you can think of it as i.e. a natural transformation, a natural isomorphism of the functor. Yeah. Actually, yeah. Sorry. That's. Let me put it. What is a generator of H and tilde SVX is the same thing as an isomorphism Z goes to H and tilde SVX. So we are taking the limits of the space of isomorphisms, well, the set of isomorphisms really, but okay. Like this, and that's just the same thing as the space of natural isomorphisms between the constant functor Z and the functor X goes here. Okay, yeah, this works. Perfect. Okay, now, what's the point? The point is that the category is a natural isomorphism in the category of functors from X to BC2, to free Z modules of rank 1. And the category of free Z modules of rank 1 is just equivalent to BC2. You have only one possible object and C2 as automorphisms. So this is a null homotopy of the map of the functor in fun X BC2, which is the same thing as maps from X to BC2, sending X to H and tilde SVX. And what I was trying to say before with saying that these action factors through the action of ON is exactly telling you that this map, this null homotopy is the null homotopy of this composite map. And this is given by the composite. X goes to BON goes to BC2. Okay. Sorry for the mess. I got a bit confused trying to prove the wrong statement. That happens, I'm afraid, more often than I would like. But okay, since I made a mess, let me go back here. So we have maps from the Thom spectrum to sigma nx, sigma nhz. That's the same thing as this limit. And I guess the neat way of saying this is that this map, the neat way of saying this is that this space of maps, sorry, SVX sigma MHZ is the same thing as the set HM is. Discrete set, and the space of generators, the subspace of generators, is the same thing as home and isomorphism from this guy. Yeah, that's what I was trying to say. And so giving a point here is the same thing as giving a null homotopy of these maps. Ooh, sorry, this was supposed to be a simple example and I made a huge mess, but okay. But what it boils down to is this notion of orientation is the same. By the way, since I am at it, let me also mention that this map here, that's always defined, and I claim an orientation is null homotopy of, also classifies a covering space, because as we have seen some time ago, maps into B sigma n are the same thing as n-sheeted covering spaces. And this is what's called the orientation space of your vector bundle, and an orientation is exactly a section of that guy, which is another way of formulating orientations of vector bundles that you might or may not have seen. But since it shows up so neatly here, I thought I'd mention it.
Okay, sorry, I have a question. So I can completely follow you, like this chain of equivalences until that Thom classes are the same thing as natural isomorphisms from the constant functor Z to this functor X to H tilde N.
Yes.
And how do you?
Okay, let me. So this is a natural transformation in functors from X to 3 Z modules of rank 1. Okay, it's a it's a mapping space in this functor category.
Mm-hmm.
And let me notice that this X is a groupoid, right? So this lands in fact in the maximal subgroupoid of this category. And so that's the same thing as fun X to BC2, because this groupoid is just BC2. Because if you have a free Z module of rank 1, you have only one possible isomorphism class and C2 as automorphisms. And that's the same thing as maps from X to BC2. And now I made a bit of a mess, but I'm arguing that this functor that goes from X to H tilde and SVX actually factors through BON, because after all, VX only depends on the point in BON. And ON is acting here exactly as the determinant. So this map corresponds to the composite X BON BC2. Okay. On the other hand, the constant map at Z is just, the constant map. It's the constant map at the base point, because Z is the base point of this groupoid. So a homotopy between these two things is exactly a null homotopy of this composite. Again, sorry for the confusion I made here. I got sidetracked and trying to prove the wrong thing for 1 second. Is this argument convincing?
Yes, I think now I can digest it later.
This is, by the way, one of those arguments that would be a lot easier if I were allowed to say the word infinity ring spectrum. Because this is essentially based on the fact this C2 here is just GL1 of Z secretly. But yeah, as I said, I'm going to follow the traditional strategy and use only homotopy ring spectra here. And let me put it, I'm already way over time. Let me put it as an exercise. R discrete ring. V is HR orientable if and only if the map X BOM BGL1 of R is null homotopic. And now you can see that when R was F2, well, not much interesting happens. And in fact, secretly, the case of HZ and the case of HF2 are the only two interesting cases, as you probably have seen before. But okay. Let me finish here and I'll start on Monday with the Thom isomorphism. And then, even if it's kind of weird because it's the very last topic and then we change slightly. But unfortunately, I didn't plan this class very well apparently. So let me stop the recording.